All right. Hi, everybody. I'm James Mickens, and today I'm going to talk to you about Atlantis, which is our new exokernel architecture for web browsers. So here's the motivation for this talk. Your web browser is a train wreck, okay? It is one of the most adversarial programming environments that Satan has ever created. Why is that? Well, the reason is that the APIs that it's supposed to implement are far too complex and too numerous for it to do so in a consistent manner. And as a result, all these web browsers are extremely brittle. And this means that it's very difficult to write robust web applications atop that very brittle infrastructure. And so in a nutshell, here's how we're going to solve this problem. We're going to take your traditional monolithic browser, which has all this code in it for doing layout, rendering, parsing, HTML, things like that. And we're going to strip that interface down. We're going to create an exokernel interface that's only responsible for doing very low-level things, rendering bitmaps, getting low-level GUI events, stuff like that. And then we're going to allow the page itself to specify its HTML parser, its DOM trees, layout and rendering engine, so on and so forth. And what's nice about this architecture is that it allows pages to manage their own complexity. So now they don't have to rely on this sort of crufty browser for their correctness. Now, I know what some of you in the audience are saying. Why do we need another browser? After all, using our current browsers, we can fetch all kinds of exciting content, like Farmville, like weird internet ads, like online dating, and pictures like this. It doesn't even matter if it's real. Now, that's all very true. But there's a dirty little secret about the web, okay? And that secret is that the Aggregate Web Protocol is actually a huge disaster. So what do I mean by the Aggregate Web Protocol? Well, browsers have to support things like HTTP, for example, to fetch the content. They have to support things like HTML and CSS to actually structure and render the presentation for that content. They have to support JavaScript for client-side interactivity. So that's both the core JavaScript spec that defines things like regular expressions, and also the DOM bindings, which allow JavaScript to interact with the rest of the browser. Now, don't forget, some people also use applets. Don't know why. So we have to throw that into the web protocol as well. And while we're talking about plugins, let's also throw in Silverlight. Let's throw in Flash. Let's throw in QuickTime. Don't forget the canvas and video tags, which are these new suggestions for how to provide rich client-side graphics. And long story short, how much time do you have? As it turns out, writing a web browser requires supporting all of these different protocols. And don't forget, if you're a web developer, you're always asking, which version of these protocols does the browser use that I'm trying to target, right? Because they're very popular deployed versions of all these protocols. So it's actually a big mess. So there are two implications to the fact that this aggregate web specification is huge. The first implication is that no single browser will ever get it right. I mean, in principle, we're told by our professors that standards give us order, right? But in practice, what happens in the web world is that there's so many standards and they're so complex that it's impossible for any single browser to provide a robust implementation of these things that will please any arbitrary web page. Now, the second consequence is that each browser will fail you in different ways, okay? And this is heartbreaking, right? So pick any two browsers, for example, you want to develop on. Firefox, IE, it doesn't matter. If you want your web page to run on both those browsers, you're dealing with two sets of implementation quirks. You're dealing with two sets of implementation deficiencies, okay? So this is extremely problematic. So here's an outline for the rest of this talk. So first I'm going to give you some case studies to show you how exactly browsers will fail you. And they will, in fact, fail you. Now, that discussion is going to motivate the design and implementation of our new Atlantis browser. I'm going to give you a few slides of implementation, and then, like all talks do, I'll give you some related work, then I'll conclude. So let me teach you a little bit about life, okay? So I go out there, I go talk to professors, and I say, look, man, these web browsers, they're terrible, they're buggy, they're ruining my life. Now, typically I tell this to the professor kind of laughs like a James Bond villain and says, James, please, calm down. When I code my web pages, I use an abstraction JavaScript library, like Jquery or something like that, that's going to hide the underlying vagaries of the platform. And basically, they accuse me of being foolish and hysterical and basically to seek professional help. So this is probably what many of you out there think, too. So you may be vaguely aware that web browsers may be a little bit quirky and cantankerous, but essentially you think they're kind of cuddly and cute, kind of like a nice old elderly couple that lives in your apartment building. And so most people think that these browsers export a largely tolerable set of browser APIs. And then what an abstraction library like Jquery can do is then take those APIs and then present a nice browser-neutral interface to your web app and to you as the web developer. So that's what you think. Now, here's the way it actually is. These browsers are murderous thieves, okay? And so what they do is they present you a flaky, semi-consistent set of APIs. And so what this means is that Jquery, or applications like Jquery, yeah, they can really tidy up the interface. It is, in fact, nicer. But the problem is that this interface is only partially browser neutral. As it turns out, Jquery cannot actually hide all of these cross-browser incompatibilities. And so I'm going to go into some detail about this. So take my hand, if you will, and join me on the garden path that I like to call why the suicide rate for web developers is 89%. Let's get started. So, James Mickens versus browsers, round one. Let's say you've got this very simple web page up here. You've got a button inside of a div inside of an HTML tag. Very straightforward, right? So what the browser does, it's going to take this HTML and form what's called a DOM tree. The DOM tree is a JavaScript data structure where you just have a node for every tag in the HTML structure. So when I click the button, there's going to be this event propagation model. Now, the standards people tell me that there's an official three-phase event model: the capture phase, the target phase, and the bubble phase. So I click on that button, and during the capture phase, the browser traces a path from that topmost HTML tag all the way down to the thing that generated the event, which in this case is the button. So the browser in the capture phase hands the event to the HTML tag DOM node, says, have you defined a capture handler? The answer is yes. So that browser executes that handler. Then it takes the event, hands it down to the div node. Div node has not defined a capture level handler. And then the browser hands it down to the button. Aha. Now we're at the target phase. This is the thing that actually generated the event. So the button has defined an event handler. The browser executes that. And now we're in the final phase, this bubble phase. So we trace that reverse path from the capturing phase. The div tag has defined a bubble handler that executes. We come up to the HTML DOM node. It hasn't defined a bubble handler. And now we're done. So here's what Papa would like. I just want support for that official three-phase event model, right? That's all that I want. Now, Firefox says, yeah, OK. Chrome's going to say, yeah, OK. IE9 is going to say, yeah, OK. IE8 says, I will not support the capture phase. Cheers. Have a happy Christmas, OK? Now, this is hugely problematic. Why does this happen? Well, this happens because different browsers have different DOM tree implementations, right? Some of these DOM trees are vibrant and full of life. They're overflowing with joy. Other of these DOM trees are somewhat more minimal, but they still possess certain tree-like characteristics. And other DOM trees are so horrifying that I don't feel comfortable discussing them in polite conversation. So, James Mickens versus browsers, event handling, part two. So, let's say I have a text box in a web browser, and I just want to enter my name in the text box. Sounds pretty simple, right? So I'm going to take my mouse, I'm going to click on that text box. That generates what's called a focus event. Okay? I'm going to type my name into that text box, then I'm going to take my mouse, move it somewhere else. That generates a blur event, or at least it should. So here's what I want. I just want the blur event. I've been told I can have it. I actually want that. What's going to happen? IE is going to tell you OK. Chrome is going to say, sometimes I'll fire that event, but sometimes I won't. You'll just have to see, won't you? And then Opera's going to say, you want a blur? I'll give you a blur. In fact, I'll give you multiple blurs. OK? Well done. Well done. Why is this? Once again, these DOM tree implementations are not completely equivalent across browsers. So let me give you a classic example of what really drives web developers crazy. So layout and rendering. What I want to do is I want to specify an element size as a percentage of the enclosing element. So in this very simple example here, I want one div that's going to be slightly smaller than the other div, as specified as a percentage of the enclosing container size, right? Basically, I want something that looks like that. Seems like a very simple thing to ask. I'm a young man in the peak of my health. Please, I don't think I'm asking for too much. Well, IE is going to say yeah. And then this is what's going to happen on Chrome and Safari. You're going to get that slight overlap there. It's almost, but it is there. And in fact, this is why it's so bad, right? Because if you're a web developer, you spend all these hours trying to make your page look nice, and you have to deal with junk like this, okay? So what do you do as a web developer? You put in all these conditional code paths in your code to say, if I'm on Firefox, do this. If I'm on IE, do this, so on and so forth. And it really kills your productivity. Why does this happen? Well, this happens because from the perspective of the web page and the developer, him or herself, the HTML, the CSS parsing, the layout engine, it's all completely opaque to that web page. Basically, you as the developer, you hand in some HTML, some CSS to this black box parser and layout engine, and then you just hope for the best. You get a DOM tree, you get a bitmap, and then whatever happens, happens. Let me give you a final example of how these browsers will ruin you. So JavaScript is a very introspective language. Okay? It defines these very powerful reflective capabilities. And so this is very nice if you want to do what's called monkey patching, if you want to add dynamically to your program some cool aspects. So for example, let's say you have this very simple application code. You define an object, and you define a function on that object. So what you can do is you can add third-party diagnostic code. So for example, from last year's NSDI, Mugshot is a logging and replay tool. And so what Mugshot does is essentially something like this. It's going to save a reference to that old method on the function. Then it's going to overwrite that function with a logging version that essentially just logs the fact, for example, that you invoke that function and then invokes that underlying function. So what do I want? All I want is the ability to use the reflection interface I've been told I can use without the crippling fear I'm going to wedge my browser. Okay? What happens? This facility is very, very fragile on all browsers. By the way, they're also dating your mom. What just happened? Question statement. Now, why does this happen? Well, the reason this happens is because there are these opaque dependencies between the C++ objects in the browser and the reflected versions in JavaScript. So suppose you have a DOM node that looks like this. That DOM node is going to define a method called addEventLister. This is how you do GUI callback registration, right? And so essentially, when you at the JavaScript layer invoke that function, you're essentially making a kernel call. Think of the browser proper as a kernel written in C++. And think of your JavaScript code as essentially working at the user layer. So you're calling some type of kernel call in there. Now, what happens is, as you can understand by now, hopefully, the browser is essentially this unfathomable beast. And so what happens is the browser has all of these internal references or pointers to stuff that exists in your world, up in the user layer. And so what this means is that when you try to use these introspection facilities, then you can only see that reference that's in red on the left. But when you start shimming things and doing crazy stuff like that, sometimes you disturb invariance amongst the references that only the quote-unquote kernel can see. Okay? And that's why this reflection interface is kind of fragile. So this raises, of course, the obvious question, how do we fix all this? And that is a natural segue to the design implementation of Atlantis. But before I can describe that, let's see where we've come from before. So this is what a traditional monolithic browser looks like. So essentially, each page instance has a process. And inside that process, you have a bunch of software modules for doing things like parsing the HTML, creating the DOM tree, stuff like that. And almost all of these components are black box with respect to the web page and the web developer. The JavaScript runtime and the DOM tree are slightly introspectable, using the interfaces I just described, but that introspection is, of course, very fragile. Now, there's been a recent trend to start looking at things like microkernel browsers. For example, this is the OP browser. So at the bottom, you have a kernel that deals with sort of low-level networking and UI type things. Then at the top level, you're going to have these strongly isolated components. Okay? So now, for example, the JavaScript interpreter is isolated from the HTML engine. Right? Now they're forced to use message passing to communicate to this kernel here. And so this is very, very nice. Right? What does this give you? This gives you improved security. But what you'll see is that these microkernel browsers use off-the-shelf components to implement things like the JavaScript interpreter and the HTML engine. So what's the implication of that? That means that there's no change in extensibility, right? Because we're still struggling with all those problems we had before with respect to these components being black box or gray box. So here's what Atlantis is going to look like. So at the bottom, we're going to have a master kernel. And this master kernel is going to be responsible for doing things like creating new frames, passing messages between the frames, and so on and so forth. Now, at the top, here's where our page instance is. And so this page instance consists of one process, but it has 3 C# app domains, okay? So we coded all of Atlantis in C#. And an app domain is essentially a way that the managed runtime can isolate code running within the same process. So think of this as a way for threads in the same process to execute in parallel, but not be able to poke each other's memory directly. And so inside each page instance, we have what's called the per instance kernel. That's going to deal with things like a UI and the network access for the particular page instance. And then up here, we have what's called the Siphon Interpreter. Siphon is just our new scripting language. It resembles JavaScript in many ways, but has some important differences. I'm going to defer you to the paper for discussion of that. But suffice it to say that the application itself, the web page itself, defines things like the layout and rendering engine and the DOM tree, and just make sure that it compiles down to this Siphon code infrastructure. So let me go into the detail. I want to go into a little bit more detail about how this all works. So I come up to Atlantis and I say, load food.html. Atlantis says, it shall be done. So Atlantis goes out and it fetches the HTML for the page. And then Atlantis is going to start scanning that page and look for a special tag called the environment tag. This is what a web page does if it wants to define its own runtime. Okay? So first, Atlantis is going to look for this compiler tag. This compiler tag is going to be the thing that takes that web page's scripting language, whether it be JavaScript, whether it be Python, whether it be whatever, and compiles that down to Siphon. So Atlantis goes out, it fetches that compiler. That compiler doesn't actually need to be written in Siphon itself. And then Atlantis installs that compiler with the interpreter. Then Atlantis goes and it finds the markup parser. This is going to be the thing that the application wants to use to parse its own markup, whether it be HTML, XML, LaTeX, heaven forbid, who knows, and use that to sort of create the rest of the application. So Atlantis goes out, it fetches that parser. In this case, that parser is written in JavaScript. Atlantis is going to feed that parser to the compiler, output a Siphon version of it, and then install that with the interpreter as well. Finally, Atlantis is going to find the runtime tag. This is the thing that's going to define stuff like maybe the DOM tree or things like that. And so Atlantis goes through the same process of fetching that code over the network and then installing it with the interpreter. Now, at this point, the Atlantis kernel steps out of the synchronous load path for the page, and it just hands the rest of the page's markup to the parser the application defined and says, go crazy. And so it's that parser that's actually going to generate things like the DOM tree or like the Ajax library, things like that. And so what will happen in that high-level runtime is that that high-level runtime can make calls through the Atlantis kernel to do things like bitmap rendering, right? That's the domain, that's the purview of the kernel. The kernel does things like creating frames, passing messages between the various frames, getting low-level GUI events, and stuff like that. Now, what happens if Atlantis comes along and it doesn't actually find one of these environment tags? Well, what happens is that Atlantis is actually going to define, by default, a backwards compatible web stack that looks just like the current web stack we have right now. But from the perspective of the application, it's written all in pure JavaScript. So this default web stack includes a JavaScript compiler, so you can call things like eval. It includes an HTML and CSS parser, an implementation of the DOM tree, stuff like that. Now, why is this default web stack nice? Well, first of all, this gives us a very clean method for handling legacy pages, right? So we can sort of load pages right off the bat. And second of all, from the perspective of the web developer, it's all made of JavaScript, right? And this is extremely nice. So now if the page wants to change the DOM tree, some aspect of it, it can just do it because that DOM tree implementation belongs to the page itself. So from the extensibility perspective, this is actually a big win. Note that in the common case, you as the web developer don't write that extensible web stack. Typically, you're going to use some off-the-shelf components. So for example, Jquery might implement the DOM tree. Microsoft might implement, I'm extremely clever, I know. Microsoft might implement your HTML parser, all these kinds of things. Because most of websites are not going to have the technical expertise or the desire to actually implement the whole thing. But what Atlantis allows them to do is take one of these off-the-shelf components and then tweak it to their heart's content. Because once again, that whole high-level application runtime belongs to the page itself. So now let me give you a couple slides of evaluation. So first, let's look at Atlantis' extensibility. Okay? So all DOM nodes have what's called an inner HTML property. This is essentially a string property that the page can assign to dynamically update the HTML content of that page. Now this is very, very convenient, but it does also allow for cross-site scripting attacks, which is not convenient and is also bad. So for example, in this first line of code, we simply get a reference to a particular DOM node called comment. This is just going to hold the text value of some type of string that the user entered. That second line of code, we're going to get a reference to another DOM node. And then in that third line, we're going to assign the inner HTML property of content parent to whatever it is that the user typed into that text box. Now, this can be a problem if the thing that the user typed into the text box is JavaScript code, right? Because then that code can run on behalf of the user. So here's what we'd like to do, right? What we'd like to do is have the ability to shim assignments to inner HTML and actually automatically invoke a sanitizer or something like that, right? And you'd think that JavaScript would allow you to do that because it gives you this nice reflection, introspection infrastructure, right? Well, this fails. This will fail in any major browser, right? And the reason why this fails is because, once again, trying to shim stuff like that, it's going to disrupt these sort of deep references that the kernel code, quote unquote, has to the rest of the application. Don't worry, though. Atlantis can help you, though. Right? Because what can you do in Atlantis? Well, in Atlantis, don't forget that that whole DOM tree implementation belongs to you. Okay? So if you as the web developer want to change it, you just reassign to inner HTML and you just do what you want to do. And in fact, we show how easy that is to do in the paper. And what's nice about this architecture is that now you don't have to wait on the browser vendor to open up an interface for doing things like shimming on inner HTML. You can just do it, right? Because that code exists totally within your own zone of control. And so here I show some page load times just to show you that we actually built something. So we have 5 pages here. We break down load times on the y-axis in terms of things like how long it takes to fetch HTML, how long it takes to parse the page. That dotted line shows the 3-second sort of load time window, after which users get a little bit irritated. And so we see that in 3 of the cases, we're sort of well below that line. In one case, we're right around that line. And in the last case, for /dot, we're roughly a second over. But we think we can actually improve performance significantly. And we go into great depths about this in the paper. But long story short, you see we're spending a lot of time on HTML parsing. And so our current version of Atlantis is not very good in terms of executing. Our function invocation overhead is actually quite high. And so HTML parsing is very intensive when it comes to that. You execute a lot of very short functions. And so we know how to fix this, and so we think this is going to be much better in the next version of the browser. So now let me briefly go over some related work before I conclude. So as I mentioned before, there's been some prior work in terms of microkernel browsers, OP, Gazelle, Service OS, things like that. And as I mentioned, what these things do is they actually give you much better security because they strongly isolate some of these components like JavaScript engines, HTML renders, things like that. Even though they give you better security, they do not give you better extensibility and better robustness from the perspective of the web page itself, because these microkernel browsers are just using standard black box and gray box off-the-shelf components. I've also mentioned Jquery, which is a very popular JavaScript library abstraction framework. Okay, there are a lot of other frameworks like this, MooTools, Prototype, stuff like that. You may have also heard of GWT or Script Sharp. These are compiled to JavaScript frameworks. So for example, GWT takes Java, compiles it to JavaScript. Script Sharp is the same thing for C#. And so once again, these are attempts to sort of get our hands around this ugly browser interface and start out at least with something that's much nicer than that. And so these things do make it much easier on the developer, but note that importantly, they can't hide all the browser quirks, for example. They can't hide that rendering bug I showed you before. And importantly, too, these frameworks can't actually make black box components introspectable. You can't just run Jquery and actually make the rendering engine introspectable, for example. So, in conclusion, we think that web browsers have a lot of potential. Now, of course, when someone tells you you have a lot of potential, that means that you're actually failing right now, okay? And so we think that web browsers actually have to be fundamentally restructured if they're going to provide a fundamentally robust platform for web applications, right? And so the reason we think that these browsers have to be restructured is because basically they've been given an impossible task, okay? They've been told to implement this whole smorgasbord of protocols over here, and it's impossible, we think. You know, no individual browser will be able to get all of these protocols right. And furthermore, each one of those browsers will have different implementation quirks that makes it very difficult to implement a sophisticated web application across multiple browsers. So what I've presented to you today is Atlantis, right? I wish I could buy this painting, by the way. I have no idea where this came from. It's amazing. So I've presented to you Atlantis. So Atlantis is an exokernel browser. And so what Atlantis does is it radically narrows the interface that the browser has to export. So the Atlantis kernel is going to handle low-level networking, GUI events. It's going to render bitmaps that the client page presents to it. And it's the application itself, the web page itself, that's allowed to define high-level abstractions like the DOM tree. And so the advantage of Atlantis is that, yes, it gives you the strong security provided by other microkernel browsers like OP, but it also gives you a powerful extensibility and introspection interface. And what this allows web developers to do is spend a lot more time thinking about the high-level semantics of their program and a lot less time thinking about the vagaries of the underlying browser they want to deploy that application to. Thank you. All right.
Hossam Abulabdeh from Cornell.
Howdy.
Hi. So how does Atlantis bode with mashups where you're getting different bits from different domains and building them into a single site? Do each one of these components have to define their own environment? And what if these environments somehow conflict with one another?
Right. So, let's start with a simple case first. Let's say you have a single frame that's going to be bringing in, let's say, JavaScript code from multiple external domains. Right. That's going to compose in the same way that it composes now. So in terms of security, the Atlantis kernel is responsible for enforcing same origin policies. So those kinds of mashups will be fine. And in general, mashups that should work in the standard world should work in the Atlantis world. I'm not sure if you had a particular example of a mashup in mind that you thought.
Well, I mean, if my site defines its own environment and its own markup, and I'm trying to take a widget from that site and embed it into another site that defines its own environment and markup.
So let's see. So if those two sites exist in different frames, then that's not a problem, because essentially there's strong isolation there, and they communicate through post message, which sort of is a immutable string communication interface. Now, in terms of within a single frame, there can only be one definition for the high-level runtime, and that's whoever is sort of the owner of that root. So that's how that would work. Thank you. Thank you.
Brian Ford, is this on? Oh, okay. Thank you for the very interesting, entertaining presentation. Now, I'm really with you on the high-level approach.
This sounds like a trap.
No. Bear me out. It seems like your current implementation has some performance challenges. And,
Yes.
this kind of begs the obvious question, did you consider using, instead of some high-level interpreted variant of JavaScript, did you consider using something like Zax or Google Native Client or something in that category as the foundation for exactly what you did?
Yeah, so that's a good question. So there's essentially a couple different claims we're making in the paper and in the talk. I mean, one claim is that the web protocol is just, it's broken, it's too big, right? We need to do something simpler. Then there's sort of the separate issue of how should you implement / architect that simpler thing, right? And so we happen to, in our particular implementation, go for a C# implementation, et cetera, and we go into the paper in some depth about some of the challenges that we found. Why didn't we go for something like Native Client or Zax? Well, note that that's certainly one sort of lower-level framework we could use to provide isolation and things like that. But we're actually interested in sort of what those abstractions are that you're actually going to present to the web developer. So you could use a NACL or a Zax container to hold and isolate some of these Atlantis components. But just moving to something like that doesn't actually answer some of these fundamental issues about what should the web developer be presented in terms of the interface. I mean, we don't want to present them just x86, right? And so that's why we didn't go down that route. We thought about some other things, and like I said, one thing. So, for example, one thing you could say is, why don't we just minimize the browser interface, but let's still write everything in C++, right? And so that would actually make some of the implementation stuff and the performance numbers better, so straight out of the box, right? And that'd still give you this sort of narrow interface. That's not an unreasonable thing to say. I think that if browsers were to go towards exokernel type interface, but they picked a different type of implementation style, I think we would be fine with that. We think that ours is reasonable, but we think that our main point is that the current web stack is just an abomination and needs to be sent to The Hague for war crimes. That's basically our number one claim.
Thanks.
Thank you.
Oliver Erlingson, Google. So great motivation. Brian actually asked already one of my questions, which was on native client, and sort of, for instance, which would allow you to come with each web page to come with its own even JavaScript interpreter and get rid of the problems there. So I wanted to sort of ask if you had considered that this already exists. There is a technology called Google Frame, which actually will allow you to, or Chrome Frame, which will allow you to actually write to the Chrome web browser and run that in IE6 and all versions of IE. So actually a web developer only has to write for Chrome. Since Chrome automatically updates, you have the latest version. So if that suggestion is not a question, well, the question might be...
This sounds like a trap?
No. The question might be, so why an exokernel? Why does the fundaments have to be small if you're only going to exercise which Chrome Frame does? You're only going to exercise a very small fraction of the underlying platform. Even in IE6, only the networking and a couple of other primitives are used from the underlying browser. The browser is very large, but it doesn't actually matter since all of your abstractions are coming from Chrome Frame.
That's true, but I think that it's actually important in terms of system building to not fall into this trap of sort of the generality trap of saying, yeah, we could do this using this tool. It doesn't quite provide the interface that we're looking for, but yeah, we could kind of shoehorn it in there. That's not the approach that we're trying to take. I mean, like I said, I think it's worthwhile to think about the fundamental types of abstractions that we want to actually present to the web developer. Now, in terms of things like the frame stuff, I think that work is very interesting, but I think that, once again, it's kind of sidestepping some of these more fundamental issues of what should that lowest level interface look like. So once again, I think that in terms of implementation, I mean, yeah, you could implement something that's somewhat similar to Atlantis using that technology, but I'm not sure that's the right level of abstraction. Right? So, for example, this is the same reason why we didn't use the JVM, for example. Right? You could do, I mean, one complaint you could get is, or that we've gotten before, is that why not just use the JVM for all this kind of stuff? Why not just ship all of your web pages as applet code, for example? And we think that the JVM sort of has the wrong abstraction layer. It's too complex. We think that's too bloated. And so, that's all.
Okay, thanks.
Thanks.
Hi, Michael Piatek from Google. I just wanted to ask the obvious performance question, which is, what is the actual overhead of doing this on the performance graphs that you showed versus some normal monolithic browser?
What is the overhead in terms
So
of...
you showed a bar chart of page load times. I'm
Yeah.
wondering what the page load times are if you use Internet Explorer, Chrome, or Firefox. What's the actual... I know it's not a performance paper, which is fine, but I just wanted to know what the actual performance penalty was.
Hey, don't be looking at all my secrets, man. Let's see here. So this will partially answer the question. So like in terms of micro benchmarks here, so this is comparing IE performance to Atlantis performance. This is normalized, okay? And so what we see here...
This graph seems very complex. I want a graph that's very simple, which is you loaded Slashdot and it took like 3 seconds. What if you loaded Slashdot in Chrome in the same environment? How long does it take?
So what you'll see there is that, I mean, we're worse, right? We're worse. And the thing is, like I said, it's because of those HTML parse times, right? And so that you'll see, for example, like for something like WordPress, I mean, we're probably going to be roughly in the order of maybe 50% worse, something like that. Now, for something like WordPress, that's actually not that big of a deal, right? I mean, for things like Slashdot, things where there's actually a lot of HTML parse time, yeah, you're right. The implementation is immature. I mean, I think we're fairly honest about that.
So you mentioned that the HTML parse time is a big factor for you. Is JavaScript execution because of the 2 levels of interpretation? Is that also, is the overhead there significant, or is it mostly HTML parsing?
Sometimes it's so this is the slide I was trying to show before you attacked my low self-confidence and told me to remove it from the screen.
My apologies.
Just kidding. Just kidding. We're still friends. We'll drink at a bar. So what this shows here is that we have a bunch of micro benchmarks here. And so long story short, if you look at those 2 things on the outermost part of it, you'll see that relative to IE, our local variable, the time it takes us to access local variables is slower. But more important, our time to invoke function calls, just that overhead, is slower. And that's actually very painful. And that's actually one of the main performance bugaboos that we have to get rid of. And we go in the paper into detail about how we think we're going to get rid of that. But you're right. I mean, it's an implementation artifact, and we think we can do better.
Okay.
Thank you.
We have to wrap it up here. Thanks. Let's thank all of our speakers.